So doing an example problem, dealing with some of the principles of nuclear physics. Let's say that I have a particle. Let's call that particle uranium-239. Okay. So I have a uranium-239, and that uranium-239 is going to kick off an alpha particle. Okay. Now, if you remember right, an alpha particle is going to have 2 protons and 2 neutrons. Okay? Where the uranium, well, let me remember what uranium is. I have the book open, so I'm going to check real quick. I think it's 92. I want to make sure. Uranium, 92. Where uranium has 92. Should have done a little more prep on this one. 92 minus 239. Oh, it's not that. Okay? So 239 kicks off an alpha particle. I'm just going to not worry about the number of neutrons and number of protons. It is 92 protons, so it's going to go down 2 on the periodic table. Nevertheless, so this alpha particle is going to be kicked off from this uranium. What I want to do is I want to determine the final velocity of both of these particles. Okay? Now there's 2 concepts I'm going to be dealing with, well 3 actually, that I'm going to be dealing with when coming up with this solution. The first is the equation for energy when dealing with nuclear particles. E equals mc squared. And we don't necessarily use m, we use another term called the mass defect. Okay, so the mass defect times c squared. That's the amount of energy that I'm going to have. Now, if you remember the mass defect, you calculate all the original particles, you calculate all the final particles, and from there you're able to determine how much matter has disappeared, has been turned into energy, and vice versa. You can get collisions and stuff like that, and you can create matter. Okay? So E equals mass defect times the speed of light squared. The other equation I need is conservation of energy. Okay? I'm going to presume that the energy is conserved. So energy initial equals energy final. So the energy initial is going to be the mass defect. This is the amount of energy that's being released into the system, and all of that energy is going to be converted into kinetic energy. Okay? So defect c squared is equal to 1/2 the mass of my alpha particle, okay, times the velocity squared of my alpha particle, minus 1/2 the mass, and it's no longer uranium. I'll go down 2 on the periodic table. Which makes it what, thorium? But it's going to be a heavy one, times the velocity of that squared. Okay? So the amount of matter I lose in this reaction is equal to the amount of kinetic energy gained by the alpha particle, and also gained, not minus, plus, the amount of energy that's gained when this degrades down to thorium. I do believe it is thorium, but I'm not exactly sure. Okay? Cool? So that's one part of the equation. I still can't solve this because I have too many unknowns. I do know the masses of these particles. I can solve that relatively easy by just using how much particles I initially start off with and how many particles I end up with. So I can get the mass values, but I don't know these velocity values because they're different from each other. Okay? So I don't have a solution there. I do have another way of solving this stuff. Okay? So I'm going to rewrite this over in the corner. So we ended up saying mass defect times the speed of light squared is equal to 1/2 1/2 the mass of my alpha particle, velocity squared, plus 1/2 the mass of my thorium, velocity squared of that thorium. And I'll put alpha here. Okay? That's what I'm left with. If you can't read it, that's fine. It's just a rewriting of that. The other idea is conservation of momentum. Because velocity is relative. We can say before the explosion, and you can barely see that, because velocity is relative, before the decay here, I can say that the initial momentum is equal to 0, meaning the final momentum is equal to 0. So what I can say is that 0 is equal to the mass of alpha times the velocity of alpha minus the mass of the thorium velocity of the thorium. Now, mind you, you're calculating the mass by looking at the original number of particles, figuring out that it's lost 2 protons, 2 neutrons to the alpha particle, and then the remaining matter is down here in this mass term. Okay? Cool? So from there, I have a solution. I can say mass alpha, velocity alpha is equal to that. Okay, and then I could take what I know about this and I can plug it into here. Okay? Or vice versa, I can plug it into here. Use a different colored chalk. It'll show up a little better. Okay? So I have mass defect, speed of light squared is equal to 1/2. I'm going to leave the alphas alone. Okay? What I am going to do is I'm going to change this. Plus 1/2. Now I want to substitute this term. I want to substitute this term for this term. So what I'm going to do is I've got to bring in a mass over a mass here. So I have mass squared over mass on this term. It'll make sense in a second. So that's going to give me okay. So this is going to be equal to mass of alpha times the velocity of alpha. So I'm just going to substitute that straight in. I'm going to end up with the mass defect is equal to 1/2 mass alpha, velocity of alpha squared plus 1/2 the mass of alpha squared over the mass of the thorium times the velocity of alpha squared. Okay? I can now do a little bit of algebra. I can pull this term out, I can pull this term out, and bring it to the front. I can bring a half term out. But in all honesty, I'm pretty much done at that point. If I wanted to simplify it, it would look something like this. Okay? Cool. And then that's my solution. So simplified, it just looks like this. Okay, because I'm going to pull a 1/2 mass times the mass of alpha times the velocity of alpha, which mass of alpha, velocity of the alpha. Oops, I have one mistake. There we go. Okay? That makes more sense. Look at the mass of alpha over here over the mass of thorium. This term all removes. So this is, I'm left with a 1. And I have a cyanide. Okay? So that's the solution. That's how you solve a problem dealing with particles that decay and to try to solve their velocities afterwards. It also gives me the solution for the energy. Once I've solved for velocity, I can determine how much energy is in the alpha particle and how much energy is in the thorium particle. Okay? That all can be solved for me that way. Cool? But that's using nuclear physics to solve a problem.